afternoon. Welcome back to Mrs. Thompson's classroom. Today we're going to be talking about logarithmic functions. This is part of our unit on inverse functions. So we did exponentials and now we're doing logs. So today what we're going to be doing is talking about how to convert between logs and exponentials, because logs are defined as the inverse of an exponential. And we're going to talk about what that means. We're going to graph them and learn what their domain is. And then we're going to just use some basic log properties and then talk about what the difference is between a common and a natural log. So let's get started. The logarithm is the inverse of an exponential. So what that means is our input and our output, our x and our y, or our domain and our range, swap places, right? That's how we found inverses. So notice the input of x becomes the output on the exponential, or the output on the log becomes the input on the exponential. So this will allow us to rewrite every log statement as an exponential. So in this case, the base is 5. So I'm going to put a 5 there. This 2, this is my output. So it will come over here as my input, and then will equal the x, because whatever was the input will now come out. Okay, so whatever the log equals becomes the exponent. Okay, in this case, my base is b, my output becomes my exponent, and then what I'm taking the log of becomes the output. We can also go the other direction and write exponentials as logs. So again, I take the b, the base, and I'm going to have log base 10. The exponent becomes the output, and the output becomes the input to the log. So here the base is 5. Okay, whatever the output is what's going to go in to the log, and whatever the exponent was is going to become the output of the log. Now that's going to help us evaluate logs. So let's just say we want to take these 3 statements. If I can rewrite the log as an exponential, then I can figure out what the value of it is. So think about it this way. This means that my base is 3. So I'm going to have 3 to some power equals 81. Well, 81 is actually 3 to the 4th, right? 3 squared is 9, then 27, and then 81. So it's to the 4th power. So that means that this log is equal to 4. The log will equal the exponent. Okay, in example 4, the base is 4. Okay, to some power will equal what I was taking the log of. Now, one thing I notice here is that the 64 is in the denominator. So that simply tells me that my exponent is going to be negative. But other than that, I still just need to figure out if 64 is a power of 4. Well, 64 is 4 cubed. So I end up with this log equaling -3, because that's what I got as my exponent. So that would be the output of the log. Okay, in example 5, I have 1/2 as my base, and it equals 8. Well, 8 would be 2 cubed. But how do I get the 2 into the denominator? Well, I simply make it flip over. So this would make, so 2 to the -3 would equal 1/8, right? It just flips over. So what this log ends up being is a -3. All right, so how do we graph these functions? Well, since we said they were inverses, let's just start by graphing the exponential and then figuring out what its inverse would be. So let's just plot some points first. If I use x of -1, I'll get 4 to the -1, which is 1/4. 4 to the 0 is 1. 4 to the first is 4. And 4 squared is 16. So if I plot those points, I get this graph here. Y equals 0 is its horizontal asymptote. Okay, so to find the inverse, what we really want to do is we want to take and flip the values here. So the y becomes the x, and the x becomes the y. Okay. And then I plot each of these points. So I'm going to have 1/4, -1, 1, 0, 4, 1. And then I'm going to connect these dots. And I notice that this has a vertical asymptote at x equals 0. So this one has, the 4 to the x has a horizontal asymptote at y equals 0. So the log has a vertical asymptote of x equals 0. Remember, the domain and the range are going to swap. Also, I notice because these are inverses, they actually are reflections about the y equals x line. So every point that I found in the exponential flipped to find its corresponding point on the log. All right, let's do one more of those. Let's say we're going to take the base of 1/2. So really what I want to do is I want to think about this as 1/2 to the y equals x. And so what I really want to do is I want to pick y values, okay, and I want to figure out what the x would be to go along with it. So if y is -1, then I will have 1/2 to the -1, which is 2. So -1, so my x of 2 gives me a -1. Okay. If y is 0, I have 1/2 to the 0, which equals 1. So I have the point 1, 0. If y is 1, I get 1/2. So I have 1/2, 1. And if it is 2, I have 1/2 squared, which is 1/4. So I have the point 1/4, 2. And again, we still have this vertical asymptote at x equals 0. Okay. Now notice this one has a base of 1/2, so this is a decay function. If the base is less than 1, just like with the exponentials, the log will be a decay. If the base is greater than 1, then it will be a growth. So in general, this is what the functions look like. So this would be b to the x, and this is log base b if the base is greater than 1, and then we have b to the x and log base b of x if the base is less than 1. So they are growth if greater than 1 and decay if less than 1. All right, so we can also graph these. This one is going to be moving to the left 1. So that means my vertical asymptote is going to move to x. Instead of being at x equals 0, it'll be at x equals -1. So I'm going to mark that to start with. Okay, and then normally we had the point 1, 0, but if I move it to the left 1, I'll end up at 0, 0. And if we normally had the point at, the base, 1, moving it to the left 1 is now at the base, 0. Well, the base in this case is 2. Sorry. Okay. Okay, and then we can connect these dots. This is a growth function because the base is greater than 1. On this one, we're doing a vertical stretch by 2, and we're moving up 1. So my vertical asymptote is staying at the 0. The point that was normally at 1, 0 is going to get vertically stretched by 2, and then it's going to move up 1. So now I have 2 times 0 plus 1, so I actually end up at the point 1, 1. Okay. We would normally have the point, since the base is 3, we would normally have the point 3, 1. So that's going to go to 3, 2, because I multiply by 2, and then I'm going to move up 1, so now I'm at 3, 3. And I'm going to go down towards the asymptote and out through that point. Notice this one just gets a little steeper because of that multiplier by 2. Okay. All right, so common log and natural log. Common log is our base 10. And so we write it just like this. So if there is no base, it is understood to be a 10. Natural log is the base e. And so we write it as ln for natural log. So you can find both, you should be able to find both of these buttons on your scientific or graphing calculator. Now, a couple of rules to note. If I take log of 10, since those bases match, it will output 1. If I do natural log of e, since that means the base and the value match, it will output 1. In fact, if I put any multiplier, power of 10 inside here, this will just equal the exponent. And the same thing here, if I take natural log of e to some power, it's just going to end up being that exponential. Okay? And logs always, if I put in a 1, I will output a 0. So they follow the same sort of rules. They're going to have the same sort of shape. So in order to calculate these, you're going to use the 2 buttons on the calculator, on my graphing calculator that are right down here. So the log of 5.6 is 0.748, and the natural log of 2.3 is 0.833. Approximately. Those are both rounded off values. Okay, but there should be a button there on your calculator. You're just going to plug it in and spit it out. Okay. Now, sometimes, though, they're going to give us, like, let's say they want us to do log of 1,000. I don't have to do this one in the calculator because I know 1,000 is 10 cubed. So my rule is, since this is base 10 of 10, it's just going to output the exponent. Also, if I do natural log of e to the fourth, natural log is base e. So if this base matches this value, it's just going to output the exponent. So sometimes we don't have to go to the calculator. Okay. All right, one application of this is the Richter scale doing earthquake measurements. The Richter scale value is the log of the intensity of the earthquake that they measure compared to or in ratio to the intensity of a zero level earthquake when nothing's going on. Okay, so if the earthquake's intensity is 10.64 times that of a zero level, okay, then the magnitude on the Richter scale is going to be the log of 10 to the 6.4 times the zero level, and then we put it in ratio to the zero level. So these cancel, and I'm left with the log of 10 to the 6.4. But this is base 10 of 10, so it just outputs. So the Richter scale value is the power of 10 that the earthquake is a multiplier of the zero level. Okay. Okay. pH values in chemistry class are also an application of logarithms, and there are other applications out there, but this is just one of them. So hopefully that gives you a little bit of an idea about logarithms. Next time we're going to talk about the properties of logs and how to calculate with them and expand and condense them and so forth. So hopefully you'll come back and join us again next time. We will see you then.